I will be talking about some other discrete probability distributions. So, the next one is the negative binomial random variable, and this is the name is very suggestive. We considered the binomial distribution, where the random variable was representing the number of successes, where the number of trials is fixed. So, you had you perform n trials, probability of success is p, and then we asked for the probability of r successes. Now, here it is the reverse. What we are saying is that independent trials are performed, probability of success is p between 0 and 1. Trials are conducted till r successes occur. So, now it is the opposite. That means, now you go on conducting the trials till r successes have occurred, and so x will be the number of trials required for r successes. Okay. In the binomial case, the trials were fixed and you had to then ask for the probability of r successes. Here the number of successes is fixed and you are saying what are the number of trials that you are required, so that r successes take place. Okay. So, therefore, if you now take, so here the random variable is the number of trials. So, probability x equal to n, and it is very simple to write it down, because so that means see, you will stop your experiment the moment you hit the rth success. So, that means up to n minus 1 trials, if I want r successes to occur in n trials, then up to n minus 1 trials r minus 1 successes should have occurred, right, and therefore, the probability of that is n minus 1 choose r minus 1. Here you are using the binomial concept, and then p r minus 1 successes, and 1 minus p n minus r failures, and then the last one is a success. So, therefore, the total number of successes add up to r, but you are here wanting r minus 1 successes to occur anywhere up to the time up to n minus 1th trial. The last trial must be, so the nth trial in this case must be a success, and so your n can vary from r because you want r successes. So, at least r trials have to be conducted. So, therefore, n is r plus 1 and so on, and this number can go on up to infinity. Now, since the experiment continues till r successes occur, so therefore, when you add up n equal to r to infinity, probability x equal to n, this must add up to 1, right, and therefore, this is a combinatorial argument to say that what we have defined here is a probability mass function. Analytically also one can show that this sum will equal 1, but then you require a little more mathematics. So, therefore, we just satisfy ourselves by giving this combinatorial argument that we will continue this trials till a success occurs, the rth success occurs, right. And also probability x equal to n is non-negative for n varying from r plus 1 and so on. So, this defines a PMF. So, this is a valid PMF. When r is equal to 1, that means, if you are just looking for the first success, then and x is the number of trials required for the first success, then obviously, you put r equal to 1. So, this becomes 0, that becomes 1, and so this is 1 minus p n minus 1 into p. That means, the first n minus 1 trials must end up in failure. So, therefore, 1 minus p raised to n minus 1, and the moment you hit a success, you stop. So, 1 minus p raised to n minus 1 into p, and n can vary from 1 onwards, right. X is now called the geometric random variable, and the corresponding PMF is the geometric distribution. Okay. Now, interesting application of a negative binomial random variable and the distribution. So, this is known as the Banach match problem. Banach was a very famous mathematician, and he was a heavy pipe smoker. So, so that he does not waste time in looking for the matchbox and then lighting up a match to light his pipe. He would carry 2 match boxes, one in his left hand pocket and the other one in the right. So, that wherever he puts his hand, he gets a matchbox, and then he lights his pipe. So, therefore, that is how he was dependent on smoking his pipe. So, each time he needed a match, he would equally likely take it from either of his pockets. It should be either of his pockets. Okay. So, it was equally likely that he would put his hand in the right hand pocket or on the in the left hand pocket. So, probability of that is the same. And now, consider the moment when the mathematician first discovers that one of his match box is empty, right. So, now assume that both matches initially carried both the match boxes, I should say. Okay. So, both the match boxes initially carried capital N matches. What is, so we are asking what is the probability that the other match box contains exactly k matches. So, that means initially both had capital N number of matchsticks in the match boxes, and then when he discovers that one of the match boxes is empty, then the other one contains exactly k matches. So, this is what we have to find out the possible probability of this event now. So, let us say that consider the case when the left hand pocket has k matches left, right. So, that means the right hand pocket is empty and the left hand pocket has the match box has k matches left. Here again I should say when the left hand pocket match box is having k matches left, right. So, I have left out the match box. Okay. Thus, the mathematician discovers the empty pocket at the, see, he emptied the n matchsticks in the right hand pocket, and here he emptied n minus k, because k are left in the left hand pocket, and then on the n plus 1th, when he put his hand in the n plus 1th, or when he takes out the match box at the n plus 1th time, from the right hand pocket, then he discovers it is empty. So, the total number of trials are n plus n minus k plus 1, right. So, exactly the situation of a negative. So, taking out a matchstick from the right hand pocket as a success. So, we will taking out as a success, we will treat it as a success. Okay. So, let us say that, yeah. So, we will say that the right hand pocket taking out or putting the hand in your right hand pocket, and of course, when you put, as long as the match box has a stick, you are also taking out a stick, a matchstick. So, therefore, whichever way you want to put it, but anyway taking out a matchstick from the right hand pocket is a success. We are looking for the n plus 1th success, but where actually he discovers that it is empty. So, that is a consequence of the match box getting emptied, but essentially what we are saying is that putting his hand in the right hand pocket is a success and putting his hand in the left hand pocket is a failure. So, random variable x, which is equal to the number of trials required for n plus 1 successes, right. So, this is exactly the case for a negative binomial distribution, and what we are saying here is that this is actually that means this is happening when you have had this many trials n plus 1 plus n minus k, and therefore, by our argument, see the last one he discovers that it is, that means at the 2n minus k plus 1th trial, he discovers that the right hand pocket match box does not have any sticks left in it. So, this will be 2n minus k n, right, if you n minus 1 r minus 1, and then 1 by 2 raised to 2n minus k plus 1. So, this will be the probability that, but then since either of the pockets could have emptied first. So, therefore, what we are saying is twice this. So, the required probability is, since either pocket can be emptied, required probability is twice of that, and so when you multiply by 2, this 1 disappears and the required probability is 2n minus k choose n into 1 by 2 raised to 2n minus k. Okay. Now, again these results I am just giving you without because handling this thing requires lot of mathematics, we will not do it. So, I will just simply say that expected value of a negative random variable which has parameters r and p, that means r number of successes are required and p is the probability of success, that is r by p, and the variance of a negative binomial r comma p random variable is r into 1 minus p upon p square. So, for example, if you are throwing off a die, the x is the random variable which is the equal to the number of throws of a die required till number 1 shows 5 times. So, your r is 5 here and p, because die we are assuming is a fair die. So, probability of each number showing up is 1 by 6. So, probability of number 1 showing up is 1 by 6. So, our p is 1 by 6, r is 5, and therefore, by these two formulae, expected value of x is 5 upon 1 by 6, which is 30, and variance, that means at least the expected value, that expected number of trials required to throws of the die required, so that number 1 shows 5 times is 30, and the variance is again by this formula comes out to be 130. 25 into 6, no, this is 150, sorry. So, this is 150. Okay. So, that is about negative binomial and geometric distribution. So, another discrete random variable which is quite useful is hypergeometric random variable, and so I will demonstrate this through an example or define this variable and the corresponding distribution. So, consider an urn containing n balls, capital N balls, out of which m are white and n minus m are black. Okay. Now, a sample of size small n is drawn without replacing the balls. Okay. That is important. The experiment is conducted without replacing the balls. So, I keep taking out the balls and put them aside, fine. So, now if x is the random variable which counts the number of white balls selected. Okay. So, sample of size n is drawn, total number of white balls are m, and so now we look at the probability of the number of white balls being equal to k. So, k can obviously vary from 0, 1 to m, because there are m white balls. Okay. So, the probability would be, now here you see we are using the multinomial distribution. So, out of m white balls you want to select k, and out of the remaining capital N minus m balls you are selecting black balls, you are selecting n minus k black balls. So, your total sample size is small n balls, right, and the total number of ways of selecting small n balls from capital N balls is n choose n, right. So, this we have already gone through how to when we were talking about the counting procedures, and so this gives you the total number of possible ways in which you can select n balls out of capital N balls, and this gives you the number of ways in which you can select k white balls from m small m white balls and n minus k black balls from capital N minus m black balls. Okay. Now, here of course, this has meaning when k is such that n minus k is less than or equal to n minus m, right, because see there is some connection between m, k and n. So, obviously, I cannot if my number m is very large, then I can select k number of balls, but then n minus k becomes negative or n minus k is so that means it has to be less than or equal to n minus m. But then see, by convention, if n minus k turns out to be greater than n minus m or n minus k is less than 0, by the convention we say that this n minus m choose n minus k is 0. So, therefore, this has a meaning. So, we do not have to worry, right, because then there will be the probability would be if k is such that n minus k is greater than n minus m or n minus k is less than 0, then these probabilities will be 0, and so there will be no mass attached with that those values of k. So, this is your this thing, and again since when we are drawing out a sample of small n balls, a white ball may appear or may not appear, and a white ball numbering 1, 2, 3 up to m may appear or may not appear. So, this takes care of all possible cases, and therefore, this is a genuine, this is a valid PMF. So, that means what we are saying is that summation probability x equal to k, k varying from 0 to m is equal to 1, and also these probabilities are all non-negative. So, therefore, this is a valid PMF. So, that this exercise we must do every time we define a random variable and its corresponding probability mass function. Now, let me just show you an example of where we make use of hypergeometric random variable and its distribution, acceptance sampling in quality control. So, what you do is, of course, the numbers here are small, but usually the numbers are much bigger than what I am using here. So, suppose 200 items in the lot, some instrument or something is being delivered by a manufacturer, the whole lot is of size 200, and the claim by the manufacturer is that no more than 10% are defective. So, this is the claim. Now, obviously, people do not have time and energy and manpower to actually inspect all the 200 items, and usually this number is very big. So, what the practice is, and that is why it is acceptance sampling. So, what you do is, after the shipment is received, a sample of size 10 is taken. Again, the numbers are all just for convenience sake, but usually there will be more realistic numbers. So, anyway, a sample of size 10 is taken without replacement, right, and if there are at most 2 defective, the lot is accepted. So, you just at random choose a sample of size 10 from this whole lot of 200 items, and then you inspect those 10 items, and you have taken out the sample without replacement. So, you inspect those, and then in that sample of size 10, if you find 0, 1 or 2 defective, you will accept the whole lot, and you will say that it is okay, and if there are more than 2 defective, then you will reject the lot. So, this is what you call acceptance sampling in quality control. Now, so let me just show you a simple computational exercise here I will do. So, that means, for example, if 5% are defective in the entire lot, then it contains 10 defective and 190 non-defective, right. So, here the claim by the manufacturer is that no more than 10% are defective. So, let me consider the case when 5% are defective in the entire lot. Then it contains 10 defective and 1, because 5% of 200 is 10. Okay. So, 10 are defective and 190 are non-defective. So, now if you want to compute the number of defectives in a sample of size 10, x is this, then you want to compute the probability that x is less than or equal to 2, which means probability x equal to 0 plus probability x equal to 1 plus probability x equal to 2. So, this is what you want to compute, and see I will just show you the calculations here. Yes. So, what I am showing you here, the probability of number of defectives being small x. So, that will be this is the case when we are assuming that 5% are defective in the whole lot, right. So, then it is 10 choose x, and then 190 are non-defective. From the non-defective I am choosing 10 minus x, and then divided by 200 choose 10, right. So, this is the hypergeometric probability of choosing x defective, or the sample size is containing x defective. Our sample size is 10, right. Hence, probability of accepting a shipment that has 5% defective. So, we are saying if at most 2 are defective in the sample size of 10. So, that probability would be probability x equal to 0, x equal to 1 and x equal to 2, which I have written down here. And if you look at the numbers, these are the 3 probabilities, you add them up and they come out to be 0.990935. That means, the probability of accepting the whole lot is 0.99. Okay. Now, if there are 10% defective, then there are 20 defective in the whole lot and 180 non-defective. Okay. So, in that case, the hypergeometric probability of x defective in your sample of size 10 would be 20 x and 20 choose x, 180 choose 10 minus x, because you are taking a sample of size 10, and divided by 200 choose 10. So, this will be the probability of having x defective in your sample of size 10, which is taken without replacement. So, therefore, in that case the probability of accepting the shipment, that is 10% defective, again we want the number of defectives in the sample to be not more than 2. So, it can be 0, 1 and 2. So, these are the numbers, and here the probability is 0.9347. So, this is less than the probability that we attained for when the shipment had 5% defective, right. Thus, the probability of accepting a 10% defective shipment is smaller than the probability of accepting a 5% defective shipment, right. So, of course, obviously, the less the defective, the more the chance of accepting the shipment, because the probability of getting 2 at most 2 defective in a sample of size 10 will be smaller if 5% are defective and when 10% are defective. This is what it is saying, and therefore, you can experiment with other values of the number of defective items in the whole lot, and then you can compute the probabilities accordingly. So, relationships among hypergeometric, binomial and Poisson distributions. So, let me show you, I have already shown you how binomial will approximate to Poisson when n is large and the number of trials is large, and your NP converges to a moderately small number. So, now here let me show you the interconnection between all these three, in fact 4 discrete random variables that we have discussed so far. Okay. So, now again we say that population is of n objects, and number of type A objects are there in the population. So, the others are not A type, and a sample of size n is drawn without replacement, right, small n. So, a sample of size small n is drawn without replacement, where of course, small n has to be between 1 and capital N, and A has to be between 0 and n. And while discussing the hypergeometric series, I told you that even if this number is bigger than this, then by convention this is 0, and so there will be no mass. So, we really do not have to worry about the values of as to what the when I am writing this, sorry, this is x. So, now if I want to, and let P be A by n, this is the proportion of item. I am not using it now, I will be using it later on. Anyway, this is the proportion of item of type A, in the original population. So, I am denoting this by P, which I will make use of later on. Now, this probability, that is your sample size of small n, contains x objects of type capital A. So, that will be choosing from small a x, right. A is the total number of type A objects you want to select. So, your sample should have x of them. So, this is A choose x, then remaining in the population n minus A are the other kind of objects. From this you are choosing n minus x other kind of objects, divided by the total ways in which you can choose a sample of size small n from capital N. Okay. Now, just write out these expressions. So, this will be A factorial divided by x factorial A minus x factorial. This will be n minus A factorial divided by n minus x factorial n minus A minus n plus x factorial. Okay. And then this is in the denominator. So, this flips over and you get here in the numerator n factorial n minus n factorial divided by n factorial. Okay. So, let us simplify this expression. What I will do is, this n factorial comes here, then x factorial and n minus x factorial. This I put together, and you can see that I am heading towards the binomial distribution. And then you see here A factorial divided by A minus x factorial. So, the terms after A minus x plus 1 will cancel out. So, you will be left with A minus 1, A minus x plus 1, right, from here, and this is gone. Then similarly here this many terms will go away. So, you will be left with n minus a minus 1 up to n minus a minus n plus x plus 1. Okay. One more from here, that will be up to that many terms. And then here similarly n factorial I have used here. Now, here n minus n factorial. So, those terms will cancel out and you will be left with n minus 1 up to n minus n plus 1. So, this is okay. From here to here, this is fine. Right. Now, what I am doing is yeah. So, this term this I can write as n choose x, right. Then from here, if I remove a from each of this, then this is a raised to x, right, because this is a minus 1, a minus x plus 1. So, x minus 1 a's come from here and this is the x at a. So, a raised to x, this comes out. Then similarly, if you remove n minus a from here, from each of them, from each of these terms n minus a. So, that will also be in number n minus x, because this is n minus x plus 1. So, when you include this one, you will get this. So, this is 1 and then this is this. So, similarly, here it would be 1. So, 1 minus 1 upon n minus a, and this is what you have. And then n raised to n we have taken, because here this is minus n plus 1. So, you take out n from each of them and divide correspondingly. So, you will have capital N raised to small n, that is this here, right. Now, what I will do is, yeah, I should have written down this step here. What I am doing is that I will write this as, oh sorry, this is this. So, I will write this as, okay, where do I, maybe I will do it here. So, this is n c x, then a by n raised to x, right, out of this, and then into divide by n. So, 1 minus a by n raised to n minus x, right. So, all this is equal to this, which is your binomial probability of choosing x items from n, and that means your number of defective or number of type A items from the sample size n is this, is probability is that. And now, this you see here, what we are saying is that x by a is small, that means a is a big number, large number, that means the number of type A objects in your total population is large. Then this number is also small and this number is also small, that means your capital N is very large. In such a situation, you can see that all these numbers go to 1, all of them, and this also goes to 1. So, this whole reduces to approximately number 1, and so this probability, hypergeometric probability of choosing a particular type of objects in your sample, that probability reduces to the binomial. Now, I should have did not probably point it out here. See, when we conduct the binomial experiment, we say that the trials are occurring independently and then you keep counting the number of successes. So, in other words, in this situation, the binomial experiment would be when you are replacing the balls, right, because getting a white ball is a success, and so in the binomial situation you replace back the ball that you have taken out. So, each time the probability remains the same of getting a white ball, which is equal to a by n, right. See here a by n p. So, this actually comes out to be this p raised to x 1 minus p raised to n minus x. So, this is what I wrote, right. So, therefore, that means the difference between a hypergeometric and a binomial is that for small values of the population size, it is without replacement the hypergeometric, right. But if you make the population size large, and as I said, all these three numbers should be small, in that case the hypergeometric reduces to is approximated by the binomial probability, right. and I have already shown you that binomial can be approximated by Poisson, where we were saying the same thing, that yes, that this should be small, right. So, in this case n into p, our p is a by capital N. So, this number should be moderately small. Then we say that for capital N being large, then we say that the binomial can be approximated by Poisson, or the binomial probability goes to Poisson. And here I have shown you that hypergeometric goes to binomial, and by the same argument that I have shown you here, when I talk about and I take lambda to be n into a by n, then you can show by again manipulating the terms that the hypergeometric will go to Poisson. And I already in the earlier lectures I have shown you that Bernoulli is binomial 1 p, right. And so, the relationship is there that when you have when you add up n Bernoulli random variables, you get the binomial. And so, this diagram shows you the relationship between the various discrete distributions that we have discussed so far. So, let us now look at the other type of random variables, which are continuous random variables. So far, we have looked at discrete random variables and their special cases. Now, I will want to describe continuous random variables, and then again we will look at the special cases of continuous random variables. So, essentially these are random variables for which possible outcomes are uncountably infinite. Okay. So, here you cannot count, and therefore, for example, if you take a subset in R 2, then the number of points is uncountable. And similarly, if you take an interval on the real line and you consider all possible real numbers, then that is an uncountable set. Okay. Examples are lifetime of a transistor. So, of course, you do not know when exactly a transistor will fail, but see, you might say that because you have finite clock. So, you can say that okay, it failed at this many but that means you can actually say that the lifetime is finite, but then it depends on your counting system. I mean, if you as fine as you make it, then the lifetime, you can treat this as a uncountably infinite. The arrival of a train at a station and so on. So, one can go on adding list to this, and as we go through this topic, we will come across so many continuous random variables. Okay. Now, one way to define a continuous random variable would be that suppose there is a non-negative function f x defined for all real x on the real line minus infinity to infinity, having the property that for any set B of real numbers, the probability that x belongs to B is integral of the function, this non-negative function f by dy over B, right. And so, here by our definition, we are saying that if x belongs to the whole real line, then the probability of that will be integral minus infinity to infinity, and f by dy is 1, right. So, we are putting this condition, and therefore, by definition f is and so f is now known as the probability density function as opposed to a probability mass function, because now this is a continuous case. So, we differentiate between the continuous and discrete by so in this case the function is probability density function, and for the discrete case we called it probability mass function. So, this is the for the random variable x. So, therefore, x is therefore if there is a function like this, and if it satisfies these conditions. So, it is a non-negative function, then we say that f is the probability density function of the continuous random variable x. Okay. So, let me give you some more idea about a continuous random variable. So, one can also define a random variable x as a variable whose distribution function is continuous everywhere. So, actually the name continuous random variable has come from here, because the distribution function of a continuous random variable is continuous. That is why we call the random variable continuous. So, actually it is not that so there is nothing about calling a random variable continuous or discrete, we actually say random variable is discrete because its cumulative distribution function is discrete. That means it has jumps, and we say that a random variable is continuous if its distribution function is f x is continuous. So, this is everywhere. That is one definition. The another one can be a random variable x is said to be absolutely continuous if there exists an integrable function f x from R to R such that f x is non-negative for all x belonging to R, and its distribution function f x satisfies the equation that f x of x is equal to minus infinity to x integral of f x t dt, x belonging to R for any real number. That means the probability x less than or equal to small x, that probability is obtained as integral of minus infinity to x f x t dt, x belonging to R. So, and then if you see that since the distribution function has the property that limit f x x as x goes to plus infinity is 1. So, therefore, you see the value of this integral minus infinity to infinity f x t dt will also be equal to 1, and hence the small function small f x that we are saying has to be non-negative is actually the PDF for the function x. So, either way, either you define it through capital F and then you say that f, the small f will be the PDF, or sometimes you may define the small PDF and then small f to be the PDF, and then you define the distribution function. Anyway, so the thing is that most of the time in this course I will not be saying absolutely continuous all the time, but whatever is absolutely continuous I will call it continuous, and then I will distinguish between a mixed random variable. So, that means a discrete random variable, mixed random variable, and continuous random variable. So, what I refer to as continuous random variable will be actually by definition absolutely continuous, because the way we have been handling, we are defining the continuous random variables and the PDFs in this course, the definition, this definition is the right one. I mean, we are following this definition that capital f x x is equal to minus infinity to x f x t dt, x belonging to R. So, whichever way, but I just thought that one needs to say a little more than what I had said in the lecture about a continuous random variable, and of course, through examples we will come to know quite a bit more about the various kinds of continuous random variables that we come across and their properties. Now, if B is an interval, then a probability x belonging to a comma b will be a to b f x dx, and that is what I am trying to show you, that if this is the curve of f x, then this implies that it is actually the area under the curve. Right, and of course, I have written it out here that in terms of your, okay, I will come to that. So, then and if a is equal to b, then this this reduces to probability x equal to a, and that means a to, so this sorry be a. So, the integral will be from a to a f x dx, and by again a definition of the integral, this is 0. So, therefore, mass at a point for a continuous random variable is 0, that or the probability that a continuous random variable assumes a fixed value is 0. This is what we are saying by this, right. And therefore, so I will come to this point, is that see the interval I have been writing as an open interval, but here I have written as closed. So, it does not matter, because whether you include the point A or the point B or both, the masses at the individual points at the fixed points A and B are 0. That means, no probability attached to fixed values of the random continuous random variable. Therefore, it does not matter whether I write it as this or as I write it as an open interval. Okay. And then so since the probability x less than or equal to x, I am sorry, this is not correct. I want to say here this is x, capital X. So, this is, so now we are defining the cumulative distribution function, or the probability that x is less than or equal to x, and this will be by our definition minus infinity to x of f y dy. So, this is the cumulative distribution function of x, and from the figure we can see that this is again f b minus f a. So, that means this will be the area from minus infinity to a under the function f x, that is f a, and then this area up to b would be f b. So, you are essentially looking for the area between the in the strip and inside this strip, right, and so this is area under the curve. Okay. So, I have shown you that for the x is a continuous random variable, then the cumulative distribution function has been defined according to this, and so we can also then have the concept of the probability in an interval a to b, and that is area under the curve. Now, let me just make emphasize 2 points here, that you see as opposed to a discrete random variable, where it was important whether in an interval, when you are talking of a probability of a random variable in an interval, then whether the endpoints are included in the interval or not. For a discrete random variable, it mattered, because every point has some positive probability, or non-negative. Now, for a continuous random variable, you see it does not really matter, because there is no concept of a probability at a point. That concept is the idea is that at a point the probability is 0. Right. So, therefore, whether I say a less than or equal to x less than or equal to b, or a strictly less than x less than or equal to b has no relevance. So, therefore, it is understood, and see that is why I am writing the integral from a to b here, right, f by dy. So, for continuous random variable, at a point there is no concept of probability or the mass, whatever you want, or the density, because it is a density. So, we measure it on an interval, fine. So, and secondly, for a continuous random variable, we will call it cumulative distribution function, that is the proper notation. And here again, if some places it may just happen that without realizing it, I may have used the word density, but does not matter. The proper notation is that it should be cumulative distribution function when your random variable x, or in fact, for this notation holds for x continuous or discrete random variable. So, the word is cumulative distribution function. We saw that for a discrete random variable, it was a summation, and here it will be in the form of an integral, because you are computing the probability of the continuous random variable over an interval. Okay. Now, we want to check that f x has the properties of a CDF, and so the first thing you want to check is that this limit of f x x as x goes to minus infinity will be 0. Okay. Yeah, so I should have said that this is equal to 0 here. Yeah, and of course, this is immediate, because limit as x goes to plus infinity would be this integral minus infinity to infinity f y dy, and since f is a probability density function, by definition minus infinity to infinity, this integral should be equal to 1. So, that part is okay. Now, for this again the argument may look repetitive, we have already used it elsewhere, but let me just repeat it. So, x n, let x n be a decreasing sequence such that x n is going to minus infinity. Now, we define the events E n, which are all points in the sample space for which capital X is less than or equal to x n. Then you see again E n, this as n goes from 1 to infinity is a decreasing sequence of events, and limit E n as n goes to infinity will be empty, because you know, as n goes to infinity, you will be talking of event where x is less than or equal to minus infinity, and so there can be no real number which is less than minus infinity, and therefore, limit E n goes to infinity is phi, is the empty set. And again, by continuity of the probability function, you will say that probability of limit probability E n as n goes to infinity is same as limit probability E n as n goes to infinity by continuity, and therefore, this will be phi, because the probability of an empty set is 0. So, this property is also satisfied, and we will verify the other properties also. And for to show that it is monotonic for a less than b, this is f x, we want to show that f x is less than or equal to f b, right. Now, since capital f x b can be written as minus infinity b, then b being bigger than a, I can break up this integral into minus infinity to a f y d y plus from a to b f. Now, this is non-negative, f is a non-negative function, this is a finite interval because b is greater than a. So, again this number is something non-negative, therefore, your probability or your f x b is bigger than f x a. Okay. And so, the function capital F is monotonic and therefore, it satisfies all the conditions for cumulative density function, and hence our definition is proper here. Now, the question, if you just define a function like this and you ask whether is it a CDF of some random variable x, then what do we all need to verify? We need to verify that for minus infinity. So, that means you need to verify that minus infinity to 0 e raised to x by 2 dx, this is equal to what? See, it should from minus infinity to infinity, it should be 1. This should no, sorry, I am showing that this is a CDF. So, this is not PDF, I mean I am not checking its PDF. So, what is happening is e raised to x by 2 limit as x goes to minus infinity, right, because this is x less than 0. So, as x goes to minus infinity, this should go to 0. So, that is fine, because x goes to minus infinity, e raised to x will go to 0. So, this goes to 0, right. Now, look at limit 1 minus e raised to x by 2 as x goes to plus infinity. So, what is happening here? This, because this portion goes to infinity. So, therefore, this is going to minus infinity and not equal to 0. So, therefore, this does not define a CDF, and so we can continue. I mean, one can try to see if any one of the condition fails to be satisfied here, we will conclude that the function that we are looking at is not a CDF. And similarly, as we have done it for the discrete case also, we check, verify when we define a continuous random variable that whether it is a valid PDF or not, probability density function. Then I will also try to later on give you examples where the random variable can be the mixed kind. That means, for some portion of the real line, it may be discrete, it may behave like a discrete random variable, and then for some points on the real, some portion of the real line, it may be a continuous random variable. Now, another thing that I want to point out is that since you are defining your CDF as this, so necessarily by the theory of integral calculus, it turns out that this has to be a continuous function. So, that is another way of differentiating between, that means for if for a certain part of the real line your CDF is continuous, then we will assume that the corresponding the part of the random variable is a continuous random variable, right. And we saw that when it is a discrete random variable, your graph of capital the CDF has jumps, and the jumps are equal to the probability of the random variable at that particular point. So, definitely, so therefore, that means you can have now CDF which is for in part a step function, and in part it is a continuous function. So, I will try to give you examples of such, and then in that case we will say that the random variable is the mixed kind. So, that means all kinds of random variables exist, discrete, mixed kind and continuous.